Chapter 3, we are going to study the mechanical properties of actually engineering materials. There are a number of materials in this world. What we are talking about is going to be steel, maybe cast iron, also the brass, the copper, the aluminum, or we also touch the fiber reinforced plastic. That is a number of material that we use in our engineering application. However, in the real world, we didn't much. We also are interested in the response of the structure. When we're talking about the structure, this is a kind of structural member. What I'm showing over here. Why we call it structural member? Because it's a kind of using the material and forming the section. This is a box section. It's produced very beautiful by the fibrous reinforced plastic. There is fiber along the length, longitudinal axis of this beam, and the yellow thing is the plastic. It's vinyl ester plastic. This called the Bluetooth fiber reinforced plastic is the technology transfer from the aerospace industry to the civil engineering industry, the construction industry. This is an example. If we like to determine the property, material property, we will cut a piece of specimen from this structural section and we test it. But if we're gonna test the whole beam like this, with this kind of section, we call structural test, different from the material test. Material test, we cut it and we test it only for the material. But this one, many times we also like to know the response. The response of what? The response of the structure under the application of the force. We do this kind of test in the structural engineering laboratory, both testing the structure and testing the material. And what kind of response? The response is going to be the behavior, how the structure or how the material respond to the applied force. Okay, and also we like to know the mechanical property of the material and mechanical property of the structure. That is the second one. This is the first one. This is the second one. And the third, usually we like to know how the structure and how the material fell, okay, under applied load. So in this kind of lab, there is going to have a lot of testing machine. For this one, we call it the UTM, Universal Testing Machine. I did tell you already. This is going to be loading frame. Loading frame. We use it for the static test of the structure. Okay, and the universal testing machine. The universal, this means it's going to be many. Okay, ways to test the material. We have some of this in our lab. Okay, we also have the loading frame. Some may have this kind of thing that is going to be very large dynamic testing. Most of the time, they test the structure and have the control system over here and hydraulic system over here. They check the structure, simulate some kind of earthquake. Okay, and In our lab, we also have this kind of thing, okay, such as this one. We have the loading frame on our F4 lab. If you like, you may go to the F4. We use this one to test some kind of structure. This is the precast, the precast industry in Thailand. Very popular. It's very popular in the past 10 years. We test the precast RC, the precast PC beam in our labs. Okay, there are a number of master degree students graduate with this kind of thing, and we also can test the column. Okay, there is a few students graduate when we test the precast reinforced concrete column, and in this one we do the measurement. What kind of measurement? The behavior, the mechanical property, and the failure can be studied from the graph. So there is two types of graph. One is the load displacement. That's usually we're talking about the behavior of the structure. Another one, if we test the material, that is going to be stress strain diagram. In this chapter 3, we use the knowledge from the first chapter, the stress and the strain, and then we will use that knowledge to determine the mechanical property of the material. For example, if we test the steel, we will have this kind of stress strain diagram. Okay, and then we analyze this. The material are going to have what kind of behavior, ductile behavior or brittle behavior, and what kind of yielding stress is going to be. For this one is supposed to be here. What kind of ultimate stress this material going to be the modulus of elasticity. We do measure this kind of mechanical property according to the Thai industrial standard, or for the international one, you may use the ASTM, American Standard for Testing and Material. And then you may use that information to prove your material property with respect to this standard, or you may use this result in the real world application. For example, in the development of the design code. So this kind of thing were very useful. And then if you test the structure, all of structure kind of big, heavy. So usually we have the crane on the top. Okay, so in our university, we also have that crane that can move, okay, along the testing frame, and it can lift a lot of things. And then when you install it, you test it, and then when it's reached the failure, this can also use to move things around. This is what we have is kind of we have a compliment from a professor from USA. That kind of frame is also I run once in civil engineering. Okay, in this one you may have the load, right, and the displacement. So most of the time when you test the structure, this called the hydraulic lamp. Hydraulic lamp. This lamp link to this one. This is going to be hydraulic pump. So some of, even though civil engineering also need to have some some kind of knowledge from mechanical engineering to design this kind of tests. And then you have this one from the hydraulic pump to measure the force. And then during the test, we study the deflection. We study the deflection of this beam. We use, for this one, we use the dial gauge to measure it. And also inside the beam, okay, we also install the stent gauge. The stent gauge over here, we attach the stent gauge to the steel to measure the steel, the strain occur in the steel during the test, okay? And then this is at the failure. We study the crack that occur on this kind of structure. So this thing used to develop the design code, okay? And most of the material testing that we do, we test according to the, for example, in Thailand, Thai industrial standard, or for the international standard, we test it according to American standard for testing and material, or ASTM. And then when do the test of the material, we will get the state strain diagram. For this one, we get P delta, that's represent the behavior, represent the failure mode of the structure. But for this one, we test it according to the standard. Okay, we set the standard for what? The standards is important. That will warranty. That will warranty the minimum mechanical property of materials that we buy it and we going to use it. If you use it in the factory, in the industrial building, in the office building, and then you have a low quality material, that material is going to be very harmful. It may cause the failure during the usage of the building or usage of your company, and then it may cause a lot of life and loss of money due to the unqualified material. So by using this, we're going to make the material as the qualified material used in engineering. We test this by using the universal testing machine, because this kind of machine can be used to test various types, such as you may do the tension test by using machine, or compression test. You just push down the material. This one is going to be the tension. This one is going to be the compression. It also can do the bending test in some kind of setup. Okay, you may put the load to the material like this. So these machines are very useful, and there are many versions of the universal testing machine in our university. This is in F5 building. It's a Trimester universal testing machine. This is about 25 years old. Okay, and we have this one. This one at the F4 building is the Instant universal testing machine. It costs about 4 million baht when we buy it. Okay, and the last one, this is going to be as the F6 sorry, F6 building is also the instant machine. This one can do the dynamic test. Dynamic test can do what so-called fatigue. We will talking about the fatigues later, fatigue test. But for this machine, usually it can do only static tests. This costs about 8 million baht, double the price of this one. So the testing machine in our engineering is kind of expensive. And again, over here we have this one. This is not the hydraulic lamp. This is going to have the load cell that's used to measure the force. And then in the machine, they have the LVDT, linear variable differential transducer, to measure the deformation of the test specimen. And then you may convert it. The stress will be P over A, and the strain will be the deformation divided by L, and then you draw the shear stress strain diagram. Okay, and there is a number of stress strain diagram. You must test if you are in civil engineering. You may need to test the round bar and the deform bar. This kind of bar are uses to reinforce the concrete. If you are in the mechanical engineering, automotive engineering, or aerospace engineering, you may test the hot loaded structural steel, even though you are the metallurgical engineering. So different Thai industrial standard apply to different type of steel that we use in our work. And let me show you 3 types of them. The first one, I'm talking about the mild steel. Review what we have previously in the last lecture. When we test for the force and we divide it by the area, and we find the deformation divided by original length, and we plot all the graph, we will have normally 2 scale of graph for some material, like for this steel. Why? Because the first portion of the graph that you can see is very stiff. It's really close to the vertical stress axis. So you got to draw another scale that is going to be this one. By what? By enlarge the horizontal scale by 100 times in order you guys can determine it. So when we test the steel, we need to find the mechanical property of this steel. The TS require you to find at least 4 of them. So these 4 are very important for you guys to know about it. The first one, you got to find the yielding stress. This is going to be the strength of the material. You're going to determine the sigma sub u. That is going to be the ultimate stress. You got to determine the modulus of elasticity. This is going to determine the stiffness. And then you got to determine the percent elongation to prove it is going to be ductile material. Okay, if you're going to use the steel. And then by doing this, we have the lecture. There are a number of mechanical property. If we require only 4 of this, the first one, the yielding. The yielding is going to be this value. We use the lower yield of the steel, represent the strength of the material. But near this point, there is some important property, such as this one is going to be stress as the what's so-called PL. PL is going to be proportional limit. Okay, and then there also the upper yielding. 3 points. These 3 points very close to each other, but we got to select one to use, and we use the sigma sub y to represent the strength of the material. And why? Because the steel has very clear yielding region. The definition of the yielding of the steel is very clear. That's why we need to use this one. And you can see all of them are very close. So we got to select one. We use the middle one. Okay, that is why. And then if you need to find the second one, that is going to be the highest stress the material can take. Okay, this one can be computed by proportional. You got to proportion like the previous one I teach you, not guess. You got to take, if this one is kind of 30 millimeter, such as this is a 30 millimeter. For what? For this one is 100 megapascal. And then you measure this. You measure this. Measure it for 10 millimeter. One maybe measure it for 9, or one maybe measure it for 11. There are some different when we talking about determining the mechanical property of the material. If you said you get 10 millimeter, so this is going to be 100 times 10 divided by the 30. You got to get it for 33.3 megapascal. So by doing that, you got the result for this one for 33.3. Most of the time, Ajahn have some range for you to determine the mechanical property of the material. Okay, and then this is the second one. And then how about the third one? The third one, you gonna determine from the slope. Okay, you may pick up any one of this because of what? Because in this region, the stress is proportional to the strain, and E is going to be the slope. So E is going to be the stress divided by the strain, and it's going to be correct up to what? Up to this proportional limit. So many times we may use sigma sub PL divided by epsilon sub PL. See over here, you got this one for 240. So that is going to be 240 megapascal. And then when you project down over here, you got to have the proportional strain of 0.0012. So you got to get this one for what? For 210 power 3 megapascal. Or you may say this is going to be 200 gigapascal. That is going to be 10 power 9 Newton per square meter. So the stiffness is very large. Okay, and then after finish the test, when you test the specimen have this kind of shape. But when you test it until it's failed, this kind of steel has the necking. Okay, so the specimen will elongate a lot, and we said by setting this is going to be L sub F, and then this is going to be L sub O. You determine the percent elongation by L sub F divided by minus by L sub O, and then you divide it by L sub O and times 100. Usually the ductile material is depend on, but for the typical structural steel, the percent ductile material should be larger than 20%. It depends on how TS specify. For higher strength material, ductile percent of elongation may be for SD 50 like 18%. But for the steel having the yielding stress 5,000 kilogram per square meter, that is 80%, right? For the steel have the yielding stress of 30,000 kilogram per square meter or 300 megapascal. The percent elongation from the TS may be 20%. Okay, it's up to the strength. Large strength have low percent elongation usually, and lower strength, lower yielding stress may have larger percent elongation. It means going to be more ductile than high strength material. Okay, that is a kind of ductile material, the steel. Okay, most of the time the steel is used to take the tension and compression, and since the property of the steel in tension and compression very similar, so most of the time it is more convenient to have the tension test. And if we come to the aluminum alloy and then we do the test, the aluminum alloy is a kind of non-ferrous material. Actually, it's supposed to have very large deformation, such as this one. The strain is very large. This one didn't have this kind of yielding. The steel have very clear. By basically, since we use a lot of steel, so the yielding stress also used for the aluminum alloy. And then since the aluminum alloy didn't have a clear yielding region, so we set up what's so-called 0.2% offset to use to determine the yielding stress of the aluminum alloy. By this one, 0.2% is 0.2 divided by 100. That is going to be 0.002. This is going to be the reference state. And then we just draw the line parallel to this region. When the line cut the curve, you project it. You get this one as the yielding strength of aluminum. Okay, this is according to the STM standard. And again, if you prefer to determine the slope of this one, you may pick up one value such as this one, and then you take the vertical line and then hit over here, and then you may project it over here. By doing this, let's say I got this one about nearly a half and do the proportion as before, and let me assume you get this one for 150 megapascal. Okay, and then this one is going to be 0.002. So the E of this aluminum is going to be 150 divided by 0.002. That is going to be 75 10 power 3 megapascal, or you may get this one for 75 gigapascal. That is a little bit 3 times lower than the modulus of elasticity of the steel. That means what? That means the aluminum has a smaller stiffness compared to the steel. Okay, and then the sigma sub u, you also can determine from the highest stress that occur from the graph, and then the percent elongation, you also can do so. The aluminum, also the ductile material, can deform a lot before it fails. Okay, coming to the other one that we have, this is going to be the cast iron. The cast iron is a kind of iron material. Okay, during the production, the steel and cast iron come from the iron ore, and then by the process, the iron ore produced to be the iron pig, and most of the time the iron pig is going to have some kind of lock or chemical, the other thing that we don't like it. And in Thailand, we don't have that kind of primary steel industry to produce the iron pick. In Thailand, we bought the iron pick from Brazil, from China, shipped to Thailand. And then Thailand has some kind of huge structural steel industry such as Siam Yamato, Thai Yamato. That is the cooperation between SCG and a company Yamato in Japan. And we also have Saviya Steel Industry in Prachuap Khiri Khan, Siam Yamato in Sapuri. And we also have Bang Sapan Steel Mill. Those kind of factories are huge industry, steel industry. And then when the iron pick come to the factory, it depends on the process. Okay, some process will transform the iron pick to be the mild steel. Okay, that is can be made to be the Lee bar, that is a round bar, or deformed bar like oil in Thailand. Or also the structural steel have the kind of I section, have a kind of T section. You can open the catalog of those companies. And also in some company put high percent of carbon into the steel to make the surface of the material harder, or you are hardened surface of the material, because in some applications such as the railway, the surface of the material are important, because in the railway the wheel of the train is steel, so the railway must has strong surface when the train brake. Okay, the braking force won't cause the failure of the surface of the railway. Okay, however, by putting the carbon into the steel, okay, you will has the micro crack in the material. So when you test this cast iron in tension, the micro crack that appear in this specimen usually is going to open. And then พวกเราครับปิดให้อาจารย์หน่อยครับ
And then ตรง iPad ไว้จะวางไว้
Warwick, you got to close your microphone. Warwick ครับ Warwick ครับ Okay, I mute you, Warwick. Okay, and then when the micro crack open, the area that's taking care of the force will reduce, and then the failure of the cast iron in tension will be abrupt. Okay, will be abrupt. That means this kind of material in tension is going to be in the brittle manner. We call this one as the brittle material. Okay, however, the same material, when you put the compression into it, the micro crack close to each other, and also there is the bug out, okay, of the material. So the area that's taking care of the force is going to be a little bit larger. So this kind of material can take very large compressive force, and then that is proper, because as the railway, the force from the wheel compress into the rail, and most of the time the cast iron used to resist the compression. This is what we have from the previous one. And then there is a lot of things that you should be understand. There is two types of the behavior of the structure, as I previously mentioned. One is going to be elastic, and another one is going to be plastic. And then if you use your plastic bag and you do some kind of experiment, when the force is low, okay, this plastic has deformation very small, the first portion. And then when you release the force, the plastic return to its original ring. This called elastic, small deformation. Okay, return to the same original height, small deformation, return to the same point. But if you hook it with the large force, you will produce what's so-called the plastic, okay, behavior. And then when you release the force, it won't go to its original ring. Okay, it still have some what's so-called the permanent set. Okay, if you pull it large, you can see it won't return to its original length even though you release the force. There is some kind of plastic behavior here. And if you pull it a lot, if you're going to tear it out, that is the failure of the material. Okay, so most of the time we use the material only in the elastic, okay, behavior in order when you build the crane, when the crane subjected to the force, the crane can defect. But when you release the force, the crane just go back. The same thing over here. Okay, if this one deform, you release the force, is return. This is elastic. And most of the time, the deformation during this kind of elastic behavior must be small. You cannot have this kind of large deformation. This also called the failure of the structure, even though the material didn't fail. Okay. Okay, we come to our conclusion that most of the time we are interested in this elastic region. And most of the time, I should tell you the strain that occur over here, usually smaller than 0.002 for the practical usage of our engineering materials. Okay, so this is going to be a kind of linear elastic when we use it in our real world application. And Hooke's law is going to be the important equation that we will use in the analysis and design of the structure. So during this one, we're going to use the material only in this region. In the elastic region, there are some important points, the same one, proportional limit, the last point where the stress strain related linearly. And then this is a small curve, but still in the elastic. Okay, that is a typical behavior. And this one is going to be the elastic limit point. And that is the last point. The behavior of the structure is going to be the elastic. And attached to it, very close to it, is going to be the yielding point. This is important because after this, the structure gonna have large deformation due to the yielding of the structure, due to the rearrangement of random grain to the one that are in order. So when they arrange the grain gonna get compact, more compact, and more compact, and in a proper arrangement. And at the end of yielding, that's usually about 40 times of the start of yielding. 20 times. That is going to be a lot larger than this. Okay, that is going to be 20 times of this. So you 20 times 0.002. That is going to be 0.0040. That is large. That's why we set the strain at the end of this yielding region or yielding strain. Ajahn, why don't we use strain over here as the yielding strain? No, it isn't the last point. That's the yielding strain end. So we got to use this one. And since it's large strain, so practically it is not good to use in the structure. Large deformation will affect the function of our structure. And then the structure will deform in this region is called the strain hardening, because the strain over here during the yielding rearrange the grain and the grain compact and the material hardened, so it can take some force until it reach the ultimate point. The sigma ultimate is need to specify because it's a kind of reserve strength. It's a kind of reserve strength of the material. That's why the TIS require you to determine it also. Okay, for example, for the steel, typical steel, the sigma sub y has 250 megapascal. Sigma sub u required to has 400 megapascal. That is reserve strength. Even though the structure has very large deformation, but it won't break into two pieces. It may not function properly, but it won't separate into two pieces. So it will prevent the loss of life, or it also prevent the loss of properties. Okay, that's why we determine the sigma sub u. And during this strain hardening, there are also some reduction of the cross section, but the reduction that's caused over here still small, cannot notice by the naked eye. But when it reaches the ultimate, you will see the necking start to occur, and in the lab we will start to see this kind of necking. So the last part of this behavior, we call it necking, because it has the change in the section for this structurality. And then the curve just stop, because the area here is going to get smaller and smaller, and then you still divide the stress by its original area, because it's going to be easy. It's very hard to measure the diameter during this kind of necking. If you see my video clips from the previous lecture, you can see this going to occur very quick in the testing. Okay, and then it's separate into two pieces over here. That is at the fracture point, and it's going to produce the fracture stress. And over here you have the fracture strength. Over here you have the ultimate strength. Okay, over here you have the yielding strength, and then over here you have the proportional strength. And then also over here you require to determine the modulus of elasticity, in which the stress divided by strength in the linear elastic region. Okay, that is what we have. And then last time we end at the Hooke's law. Okay, and what Professor Hooke found is the stress is linearly proportional strength up to the proportional limit, as I told you. And this equation is the Hooke's law. The stress equal to modulus of elasticity times the strength. And modulus of elasticity, sometimes we call it Young's modulus, in honor of Professor Young, who also the first one testing the material to determine the E. Okay, and Professor Hooks tell the relationship between the stress and the strain by the E. And then that means it's going to be the slope. And for every type of material, such as the steel with 1% carbon, this is going to be very high strength steel, high strength steel. And for this one, this is 0% carbon with heat treated. This is going to be hard steel, machine steel used to produce the machine. Structural steel, most of the time, the ME student use this kind of material. Okay, but for the CE student, we use the structural steel. And the last one is a soft steel that is typical use. Okay, and by doing this, what we have is the E indicate the stiffness. So for a typical steel, no matter percent of carbon, the stiffness of the steel are equal. And then there is some important thing about the strain hardening. I did tell you about when you test this one to the plastic region, when you release it, you will feel some of it gonna return it. So when the materials, okay, the material has high stress, you Hooke it, okay, and then when it has no stress, there is no deformation. When you pull it very small, and you release it, it's going to return its original length. This kind of behavior, we call it elastic, okay? But if you have the specimen and then you poke it with a large force and produce very large deformation, and then when you release it, what happened is the model, what happened is some of it can return to its original length, but some still stay here. Okay, if you measure this L palm and you divide it by the L palm minus L, okay, is going to be permanent set. Okay, in Thai is going to be การเปลี่ยนแปลงรูปร่างถาวร okay, and there is a small change, okay, over here. If you combine them together, this called the elastic recovery. What it means is, what I'm showing you is when you cook it, very large deformation, and when you release it, some of them is elastic recovery, and the last length L palm minus L is going to be permanent set. Okay, this portion, the structure show us the plastic behavior. Sometimes we didn't call plastic, we also call it inelastic. In is no, my, okay, is inelastic and plastic can be interchanged. And by doing this, coming into this diagram, when you load the structure in this elastic region and then you release the force, it's going to be in this model. Okay, you pull it by the force that's produce the elastic behavior. So it's going to be up and down, up and down. But when you increase the force and produce the stress that's passing to elastic region, you increase it, and that is going to produce another behavior. Okay, but anyway, you put this one to reach this point, only to reach this point, and then you release the force. When you release the force, the material will return in the different ways. It's going to return in this way. It won't return back by this curve, but it's returned by the linear elastic behavior. So when it's returned with the same slope. So we're going to have to think over here is going to be the elastic recovery. And over here, the second part of this, that is going to be the permanent set. Okay, the permanent set, that is the permanent set. By taking a look to consider this simple model, or you may pull your plastic back to understand this. Now, how do you compute the elastic recovery? Since you know the stress over here, that is going to be the stress as the A palm. Okay, that means you know the height of this one. This one is going to be sigma sub A palm, and this one is going to be the elastic recovery. It's going to related by the E. So sigma sub A palm is E, and certain recovery. So certain recovery can be computed by sigma sub A palm divided by E. Okay, I like you guys to understand this one first. And then what we are looking for is going to be certain at permanent. By doing this, since you know the total of this, okay, the strain that occur due to the force to the sigma sub A palm is going to be strain sub A palm. So the permanent strain is going to be equal to the strain at A palm, the strain due to this stress, and then minus by the strain recovery. Okay, and then you guys know that strain equal to deformation divided by its original length. By this equation, you may have the deformation equal to strain times L. So permanent deformation, or L palm minus L. Okay, permanent deformation over here can be computed by the strain permanent time this one time L. So you may measure from the lab or you may compute from the stress strain diagram. You got to have a chance to compute this thing in the examination. You got to compute this thing in the examination. You also need to find this one from the from the stress strain diagram. I also asked you in the problem T-1 also. Okay, if I'm giving you this given, okay, you can use the graph and then you can determine this one, which is the strain sub A palm, and then you also can determine the strain recovery. By doing that, you use this equation to determine the permanent strain, and later you can determine the permanent deformation. Okay, what we get from this? By doing this, the curve just change, and then this curve will has a new vertical axis, and what we have is the graph now is going to change to this one, to this black one. So by doing this, what we have, this is going to be the new point. Okay, that is going to be the new. Before this, we have only this one as the last point for the linear elastic behavior. So if we call this the yielding stress, this is going to be the old one, and the new one we're going to have this one. What we have is the material has a larger elastic region. Okay, previously we have only this one. Now we have this one is larger with a higher yielding stress. Before we have this, the new one, we have this. Okay, and also before this, we have the area. This area represents the modulus of resilience. Okay, and the new one gonna cover a larger area, so the material can absorb larger energy during linear elastic behavior. So by doing this, by doing the stand hardening, what we have is larger elastic region. Okay, higher yielding strength and higher modulus of resilience. However, there is the drawback. The material is going to be more brittle, or the material usually fell by this red flag and is changed to this yellow line. So the deformation going to be less. So it has the reduction in ductility, or in another word, it's going to be more brittle. And modulus of toughness. Modulus of toughness is talking about the area, the whole area of this one. Previously, we have this curve. Okay, so the modulus of toughness, that is the total energy the material can absorb. Since you do the stand hardening, it's going to reach this area, and then the curve just change into this new one. So by doing this, the area, okay, under the stress strain diagram going to reduce. That's why the modulus of toughness is reduced. And then we're talking about the energy. Okay, this one will prove the area under the stress strain diagram is going to be the energy per volume that structure can absorb. Strain energy, when you pull this one, and then this one has elongation, and then you release it, the energy stored in the material when you apply the force. Okay, when you apply the force, that is the energy stored. What the proof of this? Because in the elastic, if you release it, it's going to return. How is return? Because the energy release, that's why it's return. And then internal work stored in the material will equal to the external work due to the external applied force. If the material is in the linear elastic, as I said, by consider this volume, okay, and you test it, the force displacement also going to be in the linear elastic by doing this. Okay, the area under here, also the work, the area over here going to be the work. Because of what? Because work equal to force times the displacement, and since the material is the linear elastic, so the area over here represent the work. Okay, so this one will have this kind of equation. Okay, work is equal to energy that's stored in the material. Okay, that's stored in the material this is going to be external work, and this is going to be actually supposed to be the energy, and then it's going to be what? Delta P. We have sigma equal to P over A. So P is going to be sigma times A. So the P is going to be sigma times A. And A is going to be what? This is going to be, this is delta X, and this is going to be delta Y. So the area is going to be delta X times delta Y. And also you have a strain equal to delta over L. So delta equal to strain times L. Okay, so what is L? L is going to be this one. L is going to be delta Z. So you pull all of them and times it. You will have the energy, which is in the form of internal work stored in the material, is going to be 1/2 stress, okay, times this one, okay, and then we rearrange it. You can see this is going to be the volume of this small material. So it's going to be delta V. And when you divide the delta V by, delta U by delta V, you got this equation. This is going to be the in the elastic region, modulus of resilience. Okay, that is going to be the modulus of resilience. And you can use that one, the epsilon sigma equal to E epsilon, and then epsilon equal to sigma over E. When you put this one over here, you get this equation. So proof the modulus of resilience can be computed by this area. So the modulus of resilience is the ability of material that can absorb energy without permanent deformation, or is in the linear elastic region. And then this is going to be maximum 1/2 sigma proportion, strain proportion, or you may compute by this one. Another one is the ability of the material that can absorb the energy before the failure. Okay, this property is important for deciding the supporting, for example, system of the machine. The supporting system supposed to absorb the vibration due to the machine. Okay, that is important in the design in the factory. However, the modulus of toughness is the total area over here. That is important when you have the car that crash into the material. Okay, the crashing force will be absorbed by the deformation. Okay, it's changed into the energy absorbed by the material. If the material can absorb very large energy, it will be good in the design of the guardrail of the elevated highway in order to prevent the vehicle drop down from the elevated highway. So how we compute it? Last time I said it's going to be very complicated because this is the curve. Okay, but engineer is very smart. Engineer is very smart. This is going to be sigma sub u. This is going to be sigma sub y. And engineer said we can do the average between these two. We can do the average between these two. So we may compute this area, okay, by putting into the the rectangular area in which this one is going to be the strain as the failure, and this one is going to be what? Half of this sigma sub y plus sigma ultimate divided by 2. So we approximate, okay, the modulus of elasticity of a material by using this equation. It's going to be very simple, very genius for the engineer, okay? And then there are some important property, the modulus of elasticity, the yielding, okay? And then the last one you know about it is going to be the ultimate stress or strength, okay? That is important. And then they are specified in the what? These three, the TIS. There are also some other important. One is going to be the Poisson ratio. We will talking about this later. Another one is going to be the shear modulus of elasticity. We will use this one in chapter 5, but we will talking a little bit about it at the end, before the end of this chapter. Okay, and there are a number of material, that's aluminum, that cast iron, following the STM20, the concrete, the steel, okay, and the wood. So this is different kind of engine material, important one that we supposed to read this table to determine the important behavior of it, okay. And also in chapter 4 we will talking about the coefficient of thermal expansion, okay. And we will go to the example, but before we go to the example, let me stop for 5 minutes. Okay guys, come to the example. And I told you before, the learning objective of this chapter, okay, we have first one, understand the stress strain diagram. And then the second one, you should be able to determine the mechanical property, okay, the mechanical property of, for this one, steel alloy, okay. Later you will be able to use the mechanical property, able to use the mechanical property to determine the deformation of a simple structure, both elastic deformation and the plastic deformation, what we call it the permanent deformation. So we start this example by the first two. We have what? We have the stress strain diagram, okay, from the tensile test or tension test of the steel alloy. And from this one, you may notice the stress strain diagram that you have, there is two scale, one basis on the large scale on the top, okay, and another one we have is the phi scale. This is going to be the one on below it, okay, and then there you use the horizontal scale, this one for the phi scale here. This is the first one. You understand the stress strain diagram, and this stress strain diagram has no clear yielding point. When you didn't have the clear yielding point, you got to use 0.2% offset to determine it. Okay, this is the first step. You guys are supposed to understand the graph of stress strain diagram. And then they ask us to determine the modulus of elasticity, the yield stress. Okay, this modulus of elasticity and yield stress supposed to determine from this graph based on the phi scale. However, they ask us to determine the ultimate stress. It's going to be here. You're going to use this curve, which the rough scale, to determine the ultimate and the fracture stress. The ultimate is very easy. Put the ruler, okay, and draw a horizontal line. You got to draw it carefully, okay, and cut it at the point, okay. The problem is you got to use your ruler to determine this one, okay. Let's say each of this is going to be 10 millimeter, and then for this 10 millimeter is represent 100 megapascal, and one of your guys measure this, and let me assume you measure this, you get 3.5 millimeter. So that is going to be 100 times 3.5 divided by 10. So this is going to be 35. If this is 35, so this point, the sigma sub u going to be 735 megapascal. But some people may measure this for 3.6. Some measure this for 3.4. It may be some kind of a little bit different. So the final solution of this one may be in the range, not absolute number. So Ajahn will provide that to you also. Another one, you may project by using your ruler and then plotting the line that's perpendicular to the vertical axis. The same thing over here. You got to do it. And then do the same thing. Over here is 10 millimeter. You can measure this. Okay, let's say you got this one for 2.5 millimeter. So by the proportion, 100 times 2.5 divided by 10, this is going to be 25. So in my calculation, you're supposed to get this one for 600. Okay, 25 megapascal. Okay, and then for the yielding, this yielding is going to determine basis on this because the lesson above. Which one you think to use? You cannot use the rough one. Okay, you finish looking for the rough one. So you're going to use the phi scale. When you use the phi scale, 0.2 is the same as 0.2 divided by 100. So it's going to be 0.002. This is 8. Okay, not yet. 0.0024. That is too big. 0.016 in between. I believe this one supposed to be 0.002. Okay. If this one is 0.02, you mark it over here. And then you got to draw the line that parallel to the linear portion of this. And then you hit the point at A palm. And then you do the same, you do the projection of the horizontal line perpendicular to this one. And then you got this point. This is going to be sigma sub y. And again, you got to measure this one, okay? If you measure this one for, let me put it to 5.5 millimeter. So this one gonna be 55 millimeter. Sigma sub y is gonna be for 55 megapascal. Okay. And then the last one, we are looking for the modulus of elasticity. The last point that we can use to determine this one is the proportional limit. And then E is going to be sigma sub PL divided by stain sub PL. By doing this, okay, you put your ruler along the line there, and then you just draw the line that's going to be like this, and then you mark this one as the proportional limit point, and then you measure this. It's going to be something, and you measure down here. That is going to be 0.08, correct? Or it's going to be 0.016. Which one? You guys? It's going to be 0.008, or it's going to be 0.0016. Which one you're going to use? No one answer me. Which one? Which scale you're going to use? Okay, thank you. That is going to be 0.0016. Okay, and then this one is going to be 0.0016. And then you put this one, you may read it, do the same calculation basis upon this. You may measure this for 40 4 millimeter or 4.1 millimeter or 4.2 millimeter to determine it. So this one may be 300 let me 35 megapascal. If I measured it for 3.5 millimeter, it's up to you. So by doing this, let's see the PowerPoint. I should show you without the PowerPoint. So you measure this for 345. Okay, let's see. This is 345. And then it's going to be divided by 0.006. Okay, you're going to get this one for 215 gigapascal. Most of the steel may has the E in the range of 190 up to 220 gigapascal. It's just a guideline. Okay, that's a guideline for you guys to find the E. If you get the E of 70 gigapascal, the E of 70 gigapascal is not the E of the steel. Okay, that is going to be the steel. That is going to be the aluminum. If you get it 65 to 75, that is going to be the Modulus of Elasticity. That's just a guideline for you guys to check your answer. Okay, and then this one, mark the line over here and proportion over here. What do you get? 469. Quite a little bit different. But anyway, there are range. That's Ajahn will check you most of the time. Is about 5% length. Okay, up 2.5, lower another 2.5, and then that is going to be the yield stress. These two property basis on the phi scale. For the ultimate stress, you use the large scale, and then you get very close to 745. I got 735, and this one is going to be 621. Yes, I get 625. Very close to. Okay, you understand? It's going to be the length that we got to understand. Now, let us make a conclusion. Something about the real problem. Now, we have 1, 2 already. You got to be able to use the mechanical property to determine the deformation. However, the deformation can be elastic deformation, can be plastic deformation. So a big picture, when you study the stress strain diagram, you separate into elastic region and the plastic or inelastic region. Most of the time, elastic region going to be very small. In the elastic region, there is two important points: the yielding and the proportion. You got to be beware from the problem statement which one going to be, but usually they are equal. Okay, and if they just provide the yielding, use the yielding. If they provide the proportional limit, they are supposed to tell us that proportional limit is used as the yielding. Okay, and then the behavior over here, okay, when you deform it and release the force, it's to go back to the original. And then another important thing is going to be ultimate, and then the flexion. And most of the time, this first portion, like the previous example, you're going to use the phi scale. But sometimes they just provide you just one graph. Okay, if the material is has small stiffness, by doing this, they are going to ask you to determine the mechanical property. And then the second, they're going to ask you to determine the deformation. And there is two types of deformation. One is going to be in the elastic region. If you consider the stress in this elastic region, so the strain in the elastic region will be the stress divided by E. And then you will have the strain. And from the strain that you plug into this, you can target and determine the deformation, elastic deformation previously I just mentioned. And the second one, that is a little bit tricky when you load it to the plastic region. And then you will get what? You will get the plastic strain. When you get the plastic strain, the equation of strain equal to delta over L still the same. So strain as the plastic will be what? The deformation in the plastic can be determined from the strain of the plastic times L. So this is going to be another important equation. You should determine the deformation in the plastic region. And then when you release the force, the curve will not go by the original way. It will be in this way. And then we did discuss about this. We're going to have you have the elastic recovery over here. And the strain at the elastic recovery, you have stress equal to E strain, and strain equal to state divided by E. So strain recovery will be the red line. Okay, that is going to be sigma plastic divided by the slope over here, because when it's returned, the slope of this line are the same. Okay, and then there is another portion of this. That is for the strain permanent. The strain permanent going to be strain plastic divided by strain recovery. And then they're going to ask you about the permanent deformation. Okay, and it's going to be the same over here. It's going to be strain per time L. That is the whole picture of the third objective. They are going to ask you to determine the deformation that I tell you before. Okay, based on this, I like to stop and take a look at what the big picture over here and try to understand it. But if not, go directly to example. Just study how it's going to be. Okay, now we have the stress strain diagram of the aluminum, and the problem give you the modulus of elasticity. So you don't need to determine the slope over here. Okay, they given to you already. And then they ask you to determine the elongation of the bar ABC. Under the force, the bar will deform. Okay, let me put it B as the reference line. This one will deform, and another one in this side gonna have a larger deformation because the stress in the BC gonna be larger. It's subjected to 10 kilonewton. So when you leave this, you get the graph. Okay, you get the graph of the stress strain diagram. That is going to be the first one. The second one, they ask you to use this one, and then to consider the strain, you got to what? Find this one, and then they also provide you already about this one, sigma sub y. So you don't need to determine it. They provide you with the strength at 40 megapascal. They also provide you with the stiffness. So the learning objective number 2 don't need here. Okay, they didn't ask you about the mechanical property. They provide you with the mechanical properties of this aluminum. And then this is going to be the third objective. They ask us about determine this. If the load is released, do the bar return to its original length? Okay, we got to check under 10 kilonewton the behavior of the material of this bar, of this ABC bar is in which region. Okay, there is 2 portions. One is AB, another one is BC. If you cut it to determine the force, so the first one, to determine elastic or plastic, you got to determine the stress. Okay, the stress of AB and the stress of BC, and then we got to check this behavior by compare the obtained stress with the sigma sub y. If it's small, it's going to be in this elastic portion. If it's large, it may be come to this plastic region. So depend. If you like to determine the stress, so the first one, you got to draw the free body diagram, and then you use the equation of equilibrium, okay, to find what F sub AB and to find F sub BC. By doing this, you have the free body diagram. You set this one to be the Y, to be the X, and this portion subjected 10 kilonewton. And then over here, you may draw another free body diagram, and this is subjected to 10 kilonewton. And this one is the axial force. It will produce this one for F sub AB. And for this one, you may set this one axial force, and then this one will be F sub BC. Summation F sub X equal to 0. So F sub BC is going to be 10 kilonewton. The same way as this one, you do the summation of F sub X equal to 0. This one is positive. That's F sub AB is going to be 10 kilonewton. It is in tension. The same thing is in tension. And then the second step, you got to determine phi sigma sub AB, okay, and phi sigma sub BC. For sigma sub AB, you will use this one. That is going to be what? 10 kilonewton, or it's going to be this one. And then the diameter of this one is 20 millimeter for the AB. So you may use the A equal to pi r square. So you divide this one pi, and then if I like it, I use this 10 millimeter square, okay, in order to determine F sub AB. So it's going to be 100 divided by pi, okay, and then you got to get it to 31.8 That is 31.83 megapascal. That's the stress occur in this portion. And then there is this portion. And by doing this is going to be sigma sub BC again is going to be 10,000. However, the area here is smaller. It's going to be pi and then 7.5 millimeter square. That is going to be higher stress than the stress in the sigma sub BC. So it's going to be 10,000 divided by 7.5 divided by 7.5 and then divided by 3 point. It's going to be 56.59. This is going to be 56.59 megapascal. What we have now is this one is less than sigma sub y, but this one is larger than sigma sub y. This one is in elastic behavior because it's less than 40. Okay, less than 40. But this one going to be in the plastic behavior. Okay, we check it. And now what we are going to determine is what? If the load is released, do the bar return its original length? No, no, it won't. Okay. If not, what the permanent set? Okay. By doing this, we go to the third step. Okay. Let me show you by the PowerPoint. Now we arrive at this point. Keep the aluminum have the proportional limit to the yielding point. Okay. And then we understand it. We determine the sigma sub AB. Okay. And then we determine the sigma sub BC. This one is less than yielding stress. It has elastic behavior. This is larger. It have the plastic behavior. Now, the deformation is going to be like this. The elastic behavior will give small deformation, and plastic will give a large deformation. So, epsilon sub AB based on this one, sigma equal to E epsilon. So epsilon sub AB equal to sigma sub AB divided by this is given 70 gigapascal. So you just plug the value into it and compute it. That is going to be the elastic state. This is going to be the state due to the elastic behavior. Usually is very small. Okay. Next, for the plastic behavior, we cannot use this Hooke's law for the plastic behavior. We're going to use the stress strain diagram to find the strain in the plastic region or to find strain BC. So mark it to 56.0 and then you just draw the horizontal line and then you got to draw the vertical line and then you determine it by proportional. You got this strain. It's going to be 0.045. Okay, it's going to be 0.045. That is a lot larger than this one. This 045. This 0.045. 2 more O. That's it 100 times. So this plastic strain is approximately 100 times 100 times of the plastic strain. This is going to be the elastic strain. Plastic strain over here is nearly 100 times the elastic strain. So the deformation is going to be huge. And then we have the strain equal to deformation L. So the deformation is going to be strain times L. So the deformation total gonna be the deformation AB plus the deformation BC. Okay, or it's gonna be strain sub AB times L sub AB strain sub BC times L sub BC. You put it into this equation. Strain sub AB 600, strain sub BC 400. You got it for 18.3 millimeter. So the L palm is going to be 600 plus 400 plus 18.3. So it's going to be 1018.3 millimeter. That is going to be the L palm. Okay, from 1000 to 1018.3. Now you release the force. When you release the force, what happened is the AB gonna to return to its original length. But the BC won't. The BC will return some. Return some. And some won't. The part that return, we call it elastic recovery. Elastic recovery. But another part that won't return, we call it permanent deformation. Permanent deformation, or sometimes in short we just call it permanent set. Okay, and then the graph come. What happened is we got to determine the elastic recovery over here, and to determine the elastic recovery, as this one is the stress for the plastic. So you got to again draw the line over here, and again you got this one for this one is going to be strain at the plastic. Then based on this triangle, the slope here and here is the same. So sigma equal to E epsilon. Epsilon here is going to be epsilon over here. Epsilon recovery will be the stress at the plastic divided by E of aluminum. So that is going to be sigma sub BC divided by the strain, the modulus of elasticity of the aluminum. So you got the strain recovery of 0.0080. Okay, and then this is going to be the strain at the permanent. So we got to minus the pink by the green. Okay, and then you got the strain OG. We may call this one as the strain permanent. The strain permanent equal to 0.0442. And again, you may determine this one again, the strain equal to deformation times L, deformation equal to strain times L. So the permanent deformation is going to be 17.7 millimeter. Now, the new length is going to be 600 plus 400 plus 17.7. That is going to be 1017.7 millimeter. Okay, what we have is the first one is 1000, and then 1000 millimeter, the combination of this one, and then is subjected to 10 kilonewton. 10 kilonewton is have the deformation is changed to 1018.3 millimeter, and then when you release this, the force, that you have this one. And what is going to be the deformation of the recovery? Okay, that is going to be easy. It's going to be 18.3 from the previous one. It's going to be 18 point, which one? Yeah, 18.3. Okay, 18.3 minus 17.7. So you got this going to be the elastic recovery deformation. Just put this one, and then you got to have this one for 0.6 millimeter. That is for what we should have for the third learning objective. There is the other example for this one. This is also in my textbook, in my lecture note. Okay, this one we have the universal testing machine, we have the specimen, we have the original diameter of 12.5, we have the original length of 50 millimeter. Then this one will be determined. Okay, d sub o square O4 to be the area, and the stress is going to be the force divided by original area, and strain is going to be deformation divided by L sub O. And then again, they ask you to plot the graph. And when you plot the graph, you got to use a proper scale. Okay, by doing this, you plot the graph. The same as when you're going to do in your homework. Proper scale, the brown scale, and the blue scale. Now you determine the mechanical property of the material. And then later, they're giving you the structural member and ask you to determine the deformations, elastic and plastic and permanent deformation and inelastic deformation. That is